I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2 with the course code PHY 222, we are at the lecture number 2 and the topic is periodic functions. As we know that many physical phenomena in nature involve periodic motion. For example, mass attached to the spring or simple pendulum, or motion of earth around the sun, or motion of electron around the nucleus, all are examples of systems having particles moving back and forth doing a periodic motion. But such systems can be mathematically described with the help of periodic functions. In today's lecture, I will explain that how periodic functions can describe the motion of a particle which is doing a simple harmonic motion. So let's start with a simple harmonic motion and try to understand that how a periodic function can describe simple harmonic motion. So let's consider the motion of a particle on a circle. So let's say this is a circle, and we will have a coordinate system over here in order to mathematically model the motion of a particle moving on this circle. So let's have a Cartesian coordinate system. So this line, let's say, is horizontal line is called x-axis, and then we have a vertical line, let's say call it our y-axis, and then let's consider a particle P which is revolving or which is moving on this circle, and this circle is of the radius a. So now we have constructed this geometry where the point P is moving on the circle, and there is a Cartesian coordinate system, a rectangular coordinate system going through this circle in order to make a mathematical model for the description of the motion of particle P. And let's say this particle P is making an angle theta with the x-axis, and this is also called angular displacement. We will talk about this in detail later. And now we want to draw another line, a vertical line, which is parallel to the y-axis, and let's call this line RS for the sake of the description. And then imagine there is another point, let's say call it Q, and this point Q is making back and forth motion on this line RS, and actually we will see that this point Q is making a simple harmonic motion. So the motion of point Q will be a simple harmonic motion, and we will see this in a moment. But here in this geometry now you can see that we have two particles P and Q, and you can think of the particle Q as the mirror image of particle P. So just assume that this line RS is kind of mirror put in front of the point P. So when point P will be revolving on this circle, then when it will complete its one complete revolution, then you can imagine that this point Q will also complete a one complete revolution, but only vertically, and it will be moving up and down as the particle P is revolving on this circle, making a one complete revolution, and then the point Q will be making a motion up and down. So we will see that by this way we will be able to show that point P is executing a simple harmonic motion, as well as point Q is executing a simple harmonic motion. And we will also see that this point Q is only the is equal to the y component of the point P. So the y component of the motion of the point P will be exactly equal to the motion of the point Q on the line RS. So to construct the mathematical model now, or to go towards the periodic functions, which will represent this back and forth motion of point Q and as well as of the point P, we define some particular terms. For example, the first term which we want to define is an angular displacement, and then we will also define angular velocity. But let's first define what is angular displacement. So this theta over here, which you see, which is this point P is making with the x-axis, is called angular displacement. And this angular displacement we will see is maximally equal to 360 degree in this angle, but this angular displacement will be greater when the particle P will move away from the x-axis. And let's write it like theta is equal to omega t, and in this expression this theta is the angular displacement while this omega is called angular velocity. So when point P is revolving on the circle, this omega is a measure of that how fast this point P is moving, and this theta is the angular displacement. And here you can see that theta, which is the angular displacement, is equal to omega, which is the angular velocity, and t is the time. So now on this slide we have defined two terms, that is the angular displacement and angular velocity. And angular displacement is related to the angular velocity by this equation. Okay, so after defining these two basic terms, we now are able to describe the linear motion of a or linear displacement of a point Q, which is acting like a image of the point P. Since point P is moving on the circle and it is moving on two dimension, because it is moving in two dimension, as you can see on x-axis and y-axis, excuse me, but the point Q is making only the linear motion on the line RS. So in order to describe the linear displacement of point Q, as you can see that we draw this line which is parallel to the y-axis, and the maximum displacement of the point Q from the origin will be equal to this line, and this can be written as y is equal to a sine theta is equal to a sine omega t, where theta is equal to omega t, because this is only the vertical component. Here we will see that if we construct this right angle triangle over here, which we will do in the coming slide, then this vertical component is equal to the linear component, linear displacement of the point Q, and this is equal to a sine theta or a sine omega t. And now we will see that this is basically the definition of a simple harmonic motion, where this vertical displacement is represented by a periodic function. Now the sine theta is actually a periodic function. By periodic function we mean that after changing the value of theta we will get the same value, and that change in value of theta will be called the period of this function. But at least you can see over here that the linear displacement of this point Q is some kind of periodic function, in this case a sinusoidal function. So as I promised you that I will show you that the linear displacement of point Q is actually the y component or vertical component of the motion of this particle P. So here you can see that this is the x component of this right angle triangle we are completing in this circle. You see that this is the x component, horizontal component, and this is the y component or the vertical component. And if this is theta, so then we can write the expressions for the x and y component, and this will be like this, that x will be equal to a cos theta, where a is the hypotenuse of this triangle or the radius of the circle. So x will be equal to a cos of theta or a cosine of theta, and y will be equal to a sine of theta. So from here you can see now that the vertical component of the motion of the point P is equal to, which was the linear component of the linear motion of the particle Q. So in this complex plane, we call it a complex plane because it's the Cartesian coordinate is x and y, where y is the imaginary part. And so in this complex plane, x is equal to a cos of theta and y is equal to a sin of theta, or we can combine them using this complex plane. Z is equal to x plus iota or iy, where this I is actually representing the imaginary component. So if we substitute now the values of x and y from above two equations, x and y over here, then what we get is a into cos of omega t plus iota sine of omega t. So here you see that this imaginary this imaginary part is actually representing the vertical component. Well, it depends upon from the initial choice of theta, but in this case this sine omega t is actually representing the linear displacement of point q. And here we can combinedly write this as an Euler formula. Z is equal to a e into I omega t. So this is the in complex plane analysis that we have represented the motion of point P in a complex plane. Okay, so now we move towards the motion of point Q again, and want to show that this motion of point Q is a simple harmonic motion. So here you see this linear displacement of point Q could be written as Z is equal to a cos omega t plus iota sine omega t. But in this case, as I have brought back the Z, but in this case the vertical component, this vertical component is actually this imaginary part of the Z is actually representing the motion of the Q. So we see that this imaginary part of the Z is actually the linear motion of the point Q, and this is clearly a sinusoidal function or a periodic function. At the end of the lecture, I will show you that why and how this sine omega t is a periodic function. Okay, so as by definition we know that if sine omega t is a periodic function, then the motion of this point Q is a simple harmonic motion, because all those systems which are sinusoidal are actually executing a simple harmonic motion. Therefore, we now know that the motion of point Q is actually a simple harmonic motion. Okay, now we move towards to know that what would be the velocity of point Q, and it's very simple, because we in the previous slide we now know that Z is equal to a into cos omega t plus iota sine omega t. So if we differentiate this Z, or the displacement of the point P with respect to time, what we will get will be the velocity of the point Q, and then velocity will be actually the will be coming from the imaginary part of this Z or the displacement Z in the complex plane. Okay, so let's do this and differentiate the Z with respect to time. So as we know that Z is equal to a into e I omega t, a into e raised to power I omega t. So if we make this differentiation, what we will get is a into I omega, because t is here, so the derivative of exponential function is again an exponential function, and the further derivative of I omega t will give us I omega, and a is in its place, and this a is actually called the amplitude. This a is called actually the amplitude, or somehow the velocity amplitude, because this is the maximum velocity we can have, this dz by dt, so therefore it's called the velocity amplitude. And here it is if we open this Euler function again, so we will get cos omega t plus sine omega t iota sine omega t. So all these are the periodic function, but in this last function, the sine omega t is equal to cos omega, so its motion is equal to cos omega t or sine omega t plus phi, because it is only different in this angle phase, otherwise they are just equal. So so let's draw this x and y components with respect to t. If we draw this x and y components, you see that this is the y component and x component with respect to t. So what we see over here, that this is the velocity amplitude. You can see it is maximum at some particular time, the maximum amplitude or maximum velocity what we can have. And then over here we also have another thing, which is the time interval or the period of the function. This is called the period of the function, because after this much time interval we get back the same y-axis. So you can see over here the value of the y is again over here is same after this interval is passed. So that's why these are called the periodic motions, because after some time interval the position of the particle is again the same. So think of it like you are standing over here, you are standing in water waves. We will go for this example where we will think of the water waves, and if we are standing in a water and waves are passing through us, so what we see actually is a simple harmonic motion, the back and forth motion of the particles of a water. So what we see that the particles of the water just move up and down, and the waves pass through us. After some period, the particles which are at the maximum position, they go down at the minimum position and then come back to the maximum position. So we see that they regain their position after some time t, and this time t is called the period of this simple harmonic motion or of this periodic motion. So as I explained, that this is the period after which the particles actually come back to their original positions. So this was all about the velocity and the velocity amplitude of the point q, and we can also write this as a velocity of point q as dy by dt, because y was the linear displacement of the point q, and the derivative of this will give us the velocity, and it will be equal to a omega cos omega t. If you remember, it was sin omega t, and let's call a omega is equal to b. So this b is the maximum velocity what we can have, and that's why we call it a velocity amplitude. And in this simple harmonic motion, if we go towards now the kinetic energy of the point q, because we know what is the displacement, but now we know what is the velocity, and the last thing which we want to have is the kinetic energy of this point q and also the total energy. So as we know that kinetic energy of any particle is equal to half mv square. In this case v is dy by dt, so what we get is half m dy by dt whole square, which is equal to if we put the value of dy by dt over here, so what we will get is half m b square cos square omega t, and if we take it maximally, or we take omega t is equal to cos square omega t is equal to 1, we get total energy is equal to half mv square. So this is the kinetic energy and total energy of the point q, which is making the simple harmonic motion. So after describing these periodic function, simple harmonic motion and periodic motion, and now it's time to go towards two simple examples where I will show and I will explain that how periodic functions are used to describe the simple harmonic motion, or in other words the periodic motion. So in example number 1, as I already said, that imagine that you are standing in a water, and in this water there are waves produced, and you see these waves pass through you, and you see that the particles are making a simple harmonic motion, and they are making a back and forth motion. So what you exactly see is such kind of waves, that these is a kind of just wave drawn at 2 times. At t is equal to 0, when the wave is just generated, you can see its y and x components, and time t is passing through. So you see that at t is equal to 0, this is the shape of the wave, and when time is passed and we have time t, then the shape is changed. And but the interesting point is that at t at this point, we at this horizontal position, we have the value of y, and after some time and the this same point is moved over here and gain the same position. So this vt, after vt time, the two positions are the same, or two vertical positions are just the same. It means that they are making a periodic function, and as you stand in the wave, then wave particles regain their position after some interval of time. And at the first, so think of it like you are standing in the wave and you have taken two photographs, one at t is equal to 0 and one at t is equal to t. And the first photograph, you have y is equal to a sine 2 pi x by lambda, where x the horizontal position and lambda is called the period or the wavelength. So physically, when you are dealing with it, you will call it as a wavelength, but mathematically you can think of it as a period. And this sine function is actually will repeat this itself, as we have already seen over here, after some interval. And this interval is, see, this y and this y are just the same at x is equal to minus vt and at equal to x. So at this x, the value of y, and this x where x minus vt, the value of y are just the same. From here you can, just from the graph, you can see that the value of y is same at x is equal to at the position x minus vt and at x. So these two y's give you the same value. It means that this x, after subtracted with minus vt, produces the same thing, so it's a kind of periodic function. Okay. In example 2, now at the end I will explain that how periodic functions can be used to model simple harmonic motion. In this example, you can see that it's certain function, and it's a periodic function because when x added with the p, when our p added with the x, we get f of x back. So this p is the period of a function. It means that after every p interval, this function it gives us our original function back after the lapse of the period p. So that's why it's called the periodic function, and this p is the period of the function. And we know that the sine omega t is sine theta is the periodic function, sine theta or cos theta are the periodic functions, and since they represent the simple they describe the simple harmonic motion of a particle, therefore simple harmonic motion is a periodic motion. So for example, in this case, see, sine x plus 2 pi, if you put the value of 2 pi over here, you will see that this sine 2 pi is 0 and we get this sine x back. So see that this sine x plus 2 pi is a periodic function with a period 2 pi. So after each 2 pi, we get the sine value back to its original value. And similarly, another example is sine 2 pi into x plus 1 and sine 2 pi x plus 2 pi. So you can see again that the period is 2 pi. And lastly, this third example, the period is of pi by l into 2l. So we get the sine pi x by l back. So you see that these all are periodic functions, and they represent the simple harmonic motion. So in today's lecture, we have seen that how periodic functions can describe the simple harmonic motion, and this simple harmonic motion is so common in physical problems. As I already told you, that the mass attached to the spring, or the simple pendulum, or the tuning fork, all these execute a simple harmonic motion, that is a periodic motion, repeating their motion after certain interval. And what we want to do is to represent them, to represent this periodic function with the help of some kind of periodic functions. And we have discovered that the best way is to use this trigonometric function, that is sine or cos, or this is one of the good examples. In future lectures, we will use these sines and cosines functions, these trigonometric functions, to represent the periodic motion of physical systems. With this, I thank you all. And these are the references which you should consult. And with this I think